Today, we are going to dive into one of the most famous and beautiful objects in all of mathematics, the Sierpiński triangle. And it's got this amazing secret hiding inside of it, how you can get breathtaking complexity from just one super simple idea.
Just take a look at this thing. I mean, at first, yeah, it's a cool pattern of triangles, but if you look closer, you start to see that the whole shape is made up of smaller versions of itself, and those are made of even smaller versions, and it just goes on forever. It's this beautiful, infinite rabbit hole of detail.
And that really brings us to the big question, the mystery we're going to unravel today. How is it even possible to create a shape that has infinite complexity just by repeating one simple command?
To answer that, I figure the best way is for us to just build it ourselves, right from scratch. You're about to see just how easy the recipe for all this amazing complexity really is.
Okay, here it is. This is the entire instruction manual. Seriously, you start with a solid triangle, you find the halfway point on each side, connect those dots to make a new triangle in the middle, and then you just pop that middle one out. And the most important word in all of this? Repeat.
So let's start at step 0. All we have is one solid filled-in triangle. Easy enough, right? This is our starting canvas. All right, step 1. We apply that rule for the very first time. Find the midpoints, draw the lines, and take out that centerpiece. And what are we left with? 3 smaller, identical triangles sitting in the corners.
Now for step 2, we're just going to do that again. We take those 3 new corner triangles, and we apply the exact same rule to each of them. Find their midpoints, connect them, remove their centers. You can see the pattern is already starting to spread. And by step 3, it's really starting to look like something. We do the process again on all the newest little triangles, and what's cool is you can really start to see that signature look emerging, that pattern of empty spaces nested inside of each other. You know, this incredibly powerful idea, a process that just keeps calling on itself over and over again, it actually has a name. It's called recursion. It's kind of like a set of Russian nesting dolls, but for a set of instructions.
Okay, so now that we see how it's built, let's put on our math hats for a second. Let's see if we can spot a pattern in the numbers, like how many shaded triangles are there at each stage.
So let's just track it. At step 0, we had 1 triangle. Then at step 1, we had 3. At step 2, 9. Then 27, then 81. You starting to see a pattern here?
That's right. Every single time we apply our rule, we turn every shaded triangle we have into 3 new, smaller ones. The number of triangles literally triples with every step. I mean, this is classic exponential growth right here in a picture.
Okay, this is where things get really weird and kind of wonderful. As we keep doing this over and over, forever, what happens to the total amount of shaded area? And what happens to the total length of its border?
And this is the paradox. It's so cool. On the one hand, the area is disappearing. Every step, we remove a quarter of whatever area is left. So if you go to infinity, the total area approaches 0. But at the same time, because we keep punching new holes in it, we're adding more and more boundary lines. The total perimeter actually grows forever. So you end up with a shape that has almost no area, but an infinitely long border. Wild. So what do we even call a thing like this? A shape with infinite detail, a weird, paradoxical nature, all born from a simple repeating rule? Well, it turns out it's part of this incredible family of shapes called fractals. You see them everywhere, from nature to computer graphics. It's called a fractal. And the number one defining feature of a fractal is something we've actually already seen, self-similarity. All that means is if you zoom in on any part of the shape, you'll find a smaller, perfect copy of the whole thing. And you can see it perfectly right here. The entire Sierpiński triangle is built from 3 smaller, identical Sierpiński triangles. And of course, each of those is made of 3 even smaller ones, and it just keeps going. It's self-similar all the way down. All right, get ready for maybe the most mind-bending idea of them all. We're all used to thinking about dimensions in whole numbers, right? 1D is a line, 2D is a flat shape like a square, 3D is, the world. So, where does a shape like this fit in? Here's a really great, simple way to think about what dimension even is. Forget the textbook definitions for a second. Just think of it like this. Dimension tells you how much stuff there is in a shape as you zoom in on it.
Let's try it out. Think about a simple 1D line. If you double its length, how many of the original line do you need to cover it? 2. Now, a 2D square. If you double its side lengths, how many of the original squares do you need to cover it? 4. Okay, now look at our triangle. If we double its size, how many copies of the original does it take to build it? It's not 2, and it's not 4. It's 3. Something's different here.
So that relationship, the number of copies equals the zoom factor raised to the power of the dimension, gives us this really surprising little equation. For our shape, it's 3 equals 2 to the power of d. So what on earth is d? When you actually solve that equation for d, you don't get a whole number. You get about 1.585.
And that is just an incredible result. The Sierpiński triangle isn't a 1D object, and it isn't a 2D object. It actually lives in a mathematical space somewhere in between. It has a fractional dimension. It's way more complex than a simple line, but it's so full of holes it can't quite fill up a flat surface.
So where does all this leave us? We've seen how one tiny repeating rule can spawn infinite complexity and even break our basic ideas about what dimension means. It really makes you wonder, doesn't it? What other complex, beautiful things in the world around us are just hiding a simple repeating rule?